So inequalities can take many forms. Not sure if you're going to be taught linear ones, possibly linear ones to start off with. And then obviously you're going to go into many different functions. So just to start off with, right, let's do a quick inequality question. Linear is very simple because you can just treat the middle sign as an equals to sign. The only difference is that if you're multiplying or dividing by a negative number, what do? When you're dealing with inequalities, if you multiply or divide by a negative number, what happens? Like here, what's the answer? What's x equals to? So again, you're going to treat it,
A negative.
it'll be greater than, okay, greater than -7/2.
So the sign flips.
The sign flips whenever you're multiplying or dividing by a negative number. Sign flips, that's one rule. That's the only rule, to be honest. And every other time, you can treat it as an equals to sign when you're doing the math algebraically. For linear functions, anyways. For linear functions, you can just treat them as an equals to sign, except when you're multiplying or dividing by a negative number. It gets a little bit more complicated, though, if the function is not linear. Like something like this. X squared plus 1 is greater than 0, right? Something like that. So this means x squared is greater than -1. And this means x is greater than the square root of -1. What does any of this even mean? Yeah? So because you can't do this on the real number system, that is not possible. It's going to give you an error. So when you're dealing with any other function that's not linear, ideally, you want to know how to graph it. I think that's the best approach. So let me give you a quick example. X squared plus 1, right? X squared plus 1 looks like this, has a y-intercept and the vertex at +1. So what's the answer to this question? Again, know what the question's actually asking you. It's asking you, when is y positive? For which x values, okay? For which x values is the function positive, or is the function above the x-axis? Greater than 0 means above x-axis on the y. So what's the answer to this question? For which x values is the function above the x-axis? For every x value, yeah? For every x value. So the answer to this is going to be XER.
Mm-hmm.
What if it was x squared minus 1 greater than 0? So this is a plot of x squared minus 1 equal greater than 0. Um, and it looks like this. Has an x-intercept at positive and -1, has a y-intercept and a vertex at -1, and is opening up. What's the answer to this question? It's the same question. For which x values is the function above the x-axis? But the answer is slightly different. Ideas?
When x is like less than one
Yeah?
and greater than, and then less than -1.
So it's between when x is less than -1 and when x is greater than 1, yeah? In this
Mm-hmm.
range. That's when the x is above the y-axis. So there you go. That's how you'd solve a polynomial inequality. Usually we graph it because the math gets really wonky. So let's see some questions. So this section actually starts off with just equations. So they're not actually inequalities. So let's see if we can deduce this. And again, it says polynomial. How hard could this possibly be? So Amelia's family is planning to build another silo for grain storage, identical to the ones that they have on their farm. You know what a silo is? Have you ever driven past like the countryside and you'll see like this big cylindrical thing near like a farmhouse? It looks something like this.
Mm-hmm.
It's huge. It's very, very tall. That's a grain silo. That's where they store the grains. So that's what they're talking about. It's usually the shape of a cylinder, and then you have to climb like there's like a ladder on the side, and then I'm sure there's one on the inside as well, and you can climb through this. What's funny is that well, it's not really funny. It's kind of morbid, but because this is full of grains, right?
Mm-hmm.
What they do is sometimes they have to go in here for repairs or maintenance or whatever. And when someone goes in here, this is like quicksand. You know what that is, right?
Mm-hmm.
So the grain acts as a quicksand. And so the person slowly sinks down the more they struggle. So usually when you go inside a grain silo, you always go two-pair team. And if the person does fall and if he starts sinking, then obviously the best thing to do, the person is not move, right? Relax. And then you call the fire department or someone and they will pull him out. So what's the question actually? So there's a cylinder, it's a silo, and we're given what the height of the cylinder is 15 meters. It's quite tall. And we're given the volume of the cylinder, 684 pi meter cube. What are we missing? We have a cylinder, we're given the height, we're given the volume. What is one thing we're missing? The radius, okay? The radius of the
Mm-hmm.
cylinder. So that's probably the question. What's the radius of the cylinder? Let's see. Yeah. What are the possible values for the radius of the new silo? So it's not a terribly difficult question. What's the formula for a volume of a cylinder? Do you remember? Volume of a cylinder, what's the formula? It's pi r squared h. So
Mm-hmm.
volume of cylinder is pi r squared h. I'll give you a pro tip here, okay? So how did I know this? Let me just confirm that that's it. This is a grade. Oh, there's also this thing on top. So cylinder, the volume of any object, okay? The volume of any object is almost always the base area times the height, okay? So because it's a
Mm-hmm.
cylinder, there's a base area of pi r squared and there's an h. So in a silo, there's also this component, right? It's not just a pure cylinder. There's also this semicircular component on the top. What do we call this shape? Remember, we're in 3D. What would you call this shape in 3D? Or maybe the whole shape. It's a three-dimensional circle. What's the name?
A sphere.
So what's the formula for the volume of a sphere? So the volume of a sphere, I believe, is 4 pi r cubed. We're gonna double check this. This is again a grade 10 level concept. Volume of a sphere. So I was wrong. It's 4 over 3 pi r cubed. Okay, 4 over 3. So that's for a whole sphere. Here, we only have half of this, right? So how do we
Mm-hmm.
cut this into two? How do we cut this in half?
You divide it by 2.
You divide it by 2, and when you do that, you'll see that this 4 over 3 becomes 4 over 6. Okay? 4 over 3, here, I'll prove it to you. 4 over 3 divided by 2 is 4 over 3 times 1 over 2. It's 4 over 6. So that's the volume of a sphere for a for a half a sphere, for a semi-sphere. So now we have everything. We just plug it in and solve for R. So volume are these two equations. So pi r squared h was 15, plus 4 over 6 pi r cubed is equals to 684 pi. So there you go. That's our equation. How do we solve this? What's the first step? Look at the equation. We're trying to solve for r.
You can subtract 4 over 6 times pi r cubed.
4 over 6 and pi r cubed. You could subtract them. Mm, what I think we should do is probably, and again, this is gonna be something that you'll get used to. Whenever you're solving a polynomial equation, okay, polynomial equation, you wanna move everything to one side and then see from there. So what I'm gonna do is I'm gonna move this to the other side. And then we can probably take out a pi after that. Like this. You want to move it on one side so that one side of the equation is 0. So you can later do man or something if you need to.
Mm-hmm.
So here what I'm going to do is I'm going to pull out a pi. You see there's a pi here, there's a pi here, there's a pi here. You can
Mm-hmm.
pull this out of the bracket and then I'll just show it to you. When you pull it out, you'll have pi and then this whole thing equals to 0. We can get rid of the pi by dividing both sides by pi. So essentially the pi just disappears from this equation. So you're left with r squared 15 plus 4 over 6 r cubed minus 684 equals 0. Now it's even more complicated. What is the degree of the polynomial here? What's the power? Degree just means power, right? What's the highest power
3.
of? It's 3. So it's not 2. So you can't man your way out of this. For a third degree polynomial, the way we do it, this is for higher degree polynomials. The way we solve it is by setting r values equals to, in this equation, so we'll randomly pick r values that are factors of this constant here, 684. So for example, we'd plug plus minus 1, plug plus minus 2, because both of these are factors of 684. And then you keep going. Plus minus 3 goes into that. So you'd plug r as plus 1, and see whether or not this equation gives you a 0. We've done this in the past. We're not going to get too deep into this, but that's called factor theorem. And we solve higher degree polynomials using this. But what I'm going to do is I'm going to cheat and I'm going to just plot this just to see what the x-intercepts are on a graphing calculator. I'm not doing it by hand, obviously. So x squared times 15 plus 4 over 6 x cubed minus 684 equals 0. So I graph this. This is what I got. Remember, what does x represent here? X represents the radius of the silo, right? So as you can see, we got 3 x-intercepts, and I hate that I can't ping these. But it looks like it's negative 20. Again, remember, these are radiuses of the cylindrical silo. So we got negative 20, looks like negative 8 point something, and 6. So what's the actual answer to this question? Which one of these x-intercepts do you think would be a valid answer? Are all of them valid? So the cubic polynomial, it gave us radiuses of negative 20, negative 8-ish, and then 6. Which one of these is the answer to the question?
6.
6, because the other two are negative, right? And there you go.
Mm-hmm.
That's it for this question. Obviously, we cheated, but that's how you'd do something like this. It's not a question that you would want to really craft by hand because of the 684 thingy, okay? Did that make sense?
Mm-hmm.
Let me just pull it back up. So inequalities is definitely very tricky, I think. But that's just, we started off with an equation here. I'm not going to get too much into this, but this is what I meant. What's the degree of the function here? It's 3, right?
Mm-hmm.
So whenever you have a polynomial function, you want to move everything to one side of the equation, which they did. So now, to use the factor theorem or the remainder theorem, you have to pick factors of 3 and plug them into this equation to see which one gives you a 0. So here 3 is a common number, so the factors are plus minus 1, plus minus 3, and they saw that for 3, it gives you a 0, so the factor is x minus 3. Then you'd either divide by x minus 3 or you'd do synthetic division, long division or synthetic division, and you'd go from there. I want to focus on inequality, so let's pull up some inequalities. And again, most of them are going to be very, very simple. Like, look at this one. It's probably a two-step answer. How do we solve this equation for x? What will be the first step? It's a linear inequality, so it's quite straightforward. So for linear, you don't want everything on the same side. You just want to isolate the x. So the first thing you can do here is subtract 35. What's the next step?
You divide by -2 and
What
the sign
happens?
flips.
Yeah, exactly. The sign flip is so easy, right? That's it. And I don't think you're going to be doing polynomial inequality in class. You're going to be doing linear inequalities, which are very simple. Let's look at this one. So sometimes they give you a triple inequality like this one. So there's three sides to this equation. What changes? Not a whole lot. So here on the left and the right, you can't really do anything. So the only thing you could do is open the brackets in the middle. So let's try that. So 30, 6x plus 12 minus 2x. What's the last term here? When you open the bracket, what's the very last term? Plus 1 or minus 1?
It's -1.
It's minus 1. So like that. So let's clean up the middle part a bit more. So we have 6x minus 2x, it's 4x, plus 11, 46. So from here, it's quite obvious what we should be doing. This was minus 2, sorry. Minus 2, and this is plus 10. All right, what's the next step? You want to isolate the x in the middle.
You subtract 10.
Subtract 10, and then
And then you divide by 4.
easy peasy, right?
Mm-hmm.
So this is 5x 9. Cool?
Mm-hmm.
Easy peasy. Is this difficult?
No.
So we're not going to be focusing on linear, that's what I'm trying to tell you, because it is super simple, right? Let's see, how hard could it possibly get? It doesn't really get much harder than that. Um, Maybe we'll do this. Just seems interesting. So we're given a graph, and it says write down the thing modeled by the graph. Write down the inequality modeled by the graph. So there's going to be two parts to an inequality. So both of these are linear functions. So what we're going to do is we're going to come up with the equation for the linear function. For the blue line, it's very simple. What's the equation?
Three.
It's y equals 3, right? Y equals 3. What about for the red one? You're given the y-intercept and you can deduce the graph as well. Okay, so what's the slope? Remember, it's y equals mx plus b. What's the slope? So
One
for
over two.
1 over 2, so it's going to be 1 over 2x plus 1, right?
Mm-hmm.
That is the equation. So part A, write an inequality that is modeled by the graph. Mm, maybe something like this. When is the red line less than, or maybe we can even say less than equal to the red line? When is the red line equal to the blue line? Sorry. When is the red equal or less than the blue? So that's an example of an inequality. I'm sure there's many answers to this. So let's solve it. 1 over 2x is less than equal to 2. X is less than equal to 4. So that's the answer as well. Less than equal 4. Confirm the solution by solving your inequality algebraically. Already done. Graphically, you can just see that we're correct. At the x value of 4, that's when the y values are equal. Beyond that, the red line is higher. Okay?
Mm-hmm.
So again, not terribly difficult. It's just linear. Treat it like a linear function. What is going to be difficult, though, is polynomial inequality. For sure, it's going to be more difficult. But I'm not sure. Have you done cubic functions in class?
No.
No, right, all right. That's fine. So let's say you have a polynomial inequality. X squared plus 5x minus 6 greater than equal to 0. It's a quadratic. Just by looking at this inequality, at this equation, could you tell me whether or not this thing has x-intercepts? Does this function have x-intercepts? Yes or no?
It does.
It does, right? Is it opening up or down?
Up.
Up. So it looks something like this. Yeah?
Mm-hmm.
This point is not necessarily minus 6 because there's a plus 5x component. When that happens, it's not going to be the vertex. If you had this, then for sure this would be the vertex. But for this, it won't look like this. I don't know why I drew it like that. Minus 6 is not the vertex. We don't know what the vertex is yet, but it'll probably look something like this. So anyways, let's try and solve this. So how do we solve it? What do we need? We need one critical information here, which is this point and this point, right?
Mm-hmm.
How do we find those?
Man.
Yeah, you man it. And if you do it, you'll see that x plus 3, x minus 2 does the job. So that means x is negative 3 and positive 2. So the graph is
Wouldn't
slightly
it
off.
be wouldn't it be 6 and -1?
You are correct, because that doesn't actually add up to. positive 5. Yeah, this is correct. So it'll be positive 6, negative 6, and positive 1, right? Yeah. So 1 and negative 6. So what's the answer to this question? Again, when is it above the x-axis? When are the y
Mm,
values positive?
less than -6 and greater than 1.
Yes. Okay, that's it for quadratics anyways. For cubic, the thing about cubic is that you have to do it this way. You have to do it using the factor theorem, which is a little bit annoying. Same thing with quartic or any higher degree polynomials. You're always going to be doing it using the factor theorem, which is a pure grade 12 concept. So what I'm going to do is I'm going to trace back here to what I was doing last week. Yeah, so we finished off with this question. Graphing functions, I don't think we have too big of a problem with it. You just have to know what the parent functions look like and what the point mapping rule is. So again, to graph functions, you have to know this. A, F, K, X minus D plus C. You have to know what A, K, D, C does for each function. These are shifts. These are stretches or compressions, right?
Mm-hmm.
And you just have to figure it out for each individual function. We've done this many times in the past, so you can have a look at those. We're not going to do them again. Inverse relations is the next topic. We can just quickly do this. So remember, an inverse is when your x becomes your y and your y becomes your x. So if they give you points, right? If they give you points, the inverse is literally the points flipped backwards. X becomes y, y becomes x. So the y becomes your x. That's it. That is it. That's if they give you a set of points. What if they give you a sketch, a curve? How do we deduce inverse functions from a sketch? Remember? Inverse is simply a function that's reflected where? Inverse is just a reflection. Do you remember on what axis?
Um,
Y equals x, okay? Inverse is a reflection. Y equals x-axis. Y equals x means this line here,
mm-hmm.
the origin line, right? So let's see. It says match the inverse relation to their corresponding function. So both the original function as well as its inverse are given to us. So we just have to match them, right? How hard could it possibly be? So here, let's look at A. So your inverse line looks like this. So when you flip this, you'll see that you get something. I'm not going to be super precise here. Actually, you could be super precise. You see how this goes through 0, -2? That means our inverse function must go through -2, 0. You see how this goes through 4, 0? Our inverse function must go through 0, 4. And then you simply connect the dots. and you extend them in both directions. And there you go. That's the inverse. Very simple. Yeah?
Mm-hmm.
What's the answer to C? Sorry, let's do B. So for B, you have four options here. Which one do you think is its inverse? For A, it's D. What's the inverse of B? Let's find one point, right? Find a boundary point and see how it changed. So right now, this is going through 0, comma 2. So you know, so it must go through 2, comma 0, right? If this goes through 0, comma 2, the inverse
Mm-hmm.
function must go through 2, comma 0. So the answer to B is F. And that means C, just by the power of elimination, must be E. Okay?
Mm-hmm.
So that's inverses through um a sketch. It's quite simple. What about through an equation? How do we find the inverse through an equation? Do you remember that? Inverse through an equation is you have to switch the x and the y. Yeah. Okay?
Mm-hmm.
So again, for an ordered pair like a point, you just simply switch the x and the y. For a graph, you reflect it on the axis. For an equation, your x becomes your y, and then your y becomes your x, and then you have to solve for your new y. You'll see what I mean. So part A, find the ordered pair for f4 on the function. That just means we're giving you the x value of 4, what's the y value? So you have f of 4 is equals to 2 times 4 cubed plus 1, 64, 128, that's going to be 129. Therefore, the answer to A is 4, comma 129. Easy peasy. Part B. Find the ordered pair on the inverse relation that corresponds to the ordered pair. So what's the inverse of this coordinate that we have?
You just flip it.
You just flip it. So it becomes 129, 4, right? Easy peasy.
Mm-hmm.
Part C. Find the domain and range of f. It's easier than you think. It's a cubic function. What's the domain and range of f? So right, let me draw it. So cubic function looks like this. Goes through the origin. What do you think the domain is for this?
XER.
XER. What do you think the range is for this?
YER.
YER. Easy peasy, okay?
Mm-hmm.
Now, when you do domain and range of an inverse function, so let's say that this is f, for an f inverse, the domain becomes the range, and the range becomes the domain. So in this question, not much is gonna change. Domain is gonna be XER because the range is YER, and the range is gonna become YER because the domain is XER. So that would be the answer to part D, okay?
Mm-hmm.
Part E is the inverse relation of function. Okay, we don't know what the inverse relation looks like. I'm sure there's better ways to do it, but what we're gonna do is we're actually gonna find the inverse of this. So this is our cubic function. Our goal is to find y inverse. So here are the steps. Step number 1, your x becomes your y, and your y becomes your x. So your equation would look like x equals 2y cubed plus 1. And then from this new equation, you wanna solve for your new y, the y you just created. You wanna isolate it. By solve, I mean you wanna isolate it. So how do we solve for y here? So y is on this side of the equation. We want to get rid of that 2. We want to get rid of that plus 1. We want to get rid of that cube.
Can you
Which one?
subtract 1?
Subtract 1, yeah,
And then you divide by 2.
and then
Cube root.
cube root. So this right here is our y inverse. Now it's not obvious from the equation whether or not it's an inverse function. So what we're gonna do is we're just gonna plot this. Ideally, the best way to do this is to just graph your parent function. And then from your parent function, what you do is you flip the points. Because a cubic function is pretty easy to graph. Then you just do, you just flip x and y is what I'm trying to say. So this function looks like this. Is this a function?
Yes.
Yes, looks like it is. Right? The only place where it could fail is here, but I think it's just crossing it. All right, here's a pop quiz time, okay? Here's a pop quiz time. Notice how up until 1, 0, the curve is opening up. It's concave up, but past 1 comma 0, it's opening downwards. It's concave down. Yeah?
Mm-hmm.
So this point, 1 comma 0, is when the concavity of the plot changes. What is this point called? We briefly talked about this when we were doing second derivatives. It starts with the letter I. It's called point of something. I is what it starts off with. It's called a point of inflection. Okay, inflection.
Mm-hmm.
So that's when the concavity changes from concave up to down or vice versa. That's when the second derivative is set to equal to 0. We can just quickly do that as well. Notice it was at 1, 0, right? So this was our function. The first derivative is 6x. The second derivative is just 6. Sorry, it's 12x, right?
Mm-hmm.
When you set this equal to 0, you'd see that x is going to be equal to 0. Anyways, the inverse is a function. Not too difficult. Yeah?
Mm-hmm.
Yeah, what about this one? It's a very common question. X squared minus 1. The question is the inverse a function? I'm going to show you the long way of doing this, and I'm going to show you the short way of doing this. The short way is just a way to verify, okay? It's not a way to earn points on the exam or on an assignment, but it is very effective. Here, let me show you the shortcut way. The shortcut way is this. If it fails, if f fails, f is your primary function, fails not the vertical line test, the horizontal line test, then f inverse is not a function. So for this, is the inverse a function or no? Just by looking at the curve, by looking at the horizontal line test. Horizontal
It
line,
is a function.
it is not a function because horizontal line test crosses it twice, okay? So it is not a function. We could have used this to deduce the cubic function in the previous question as well. For that function, it checks out everywhere. So it was, but here, the quadratic, it fails, yeah? So we know for a fact that this is not a function. But let's prove it. But remember this shortcut rule. If it fails the horizontal line test, it is not a function. I want to find the equation of the inverse function. How do I find the equation of the inverse? No, do you remember the first step? Finding the inverse through an equation. You have to flip the variables.
Mm-hmm.
So x becomes y and y becomes x. Okay, that's step number one. So you have x here as y and x like this, -1. X squared -1. Step number one. Step number two, you're going to solve for the y. And that y, okay, that y will become your y inverse, your inverse function. So how do we solve for y?
You
Well,
add one,
it's very simple, right? We're not going to waste time. You add one, and then what?
you do root of 2 to square root.
So like this? Does that seem right? Go away, Cortana. Go away. Okay. Like that, does that seem right?
No,
What's missing? So we had y squared is equals to x plus 1. What's y gonna be equal to? It is gonna be the root of x plus 1, but it's missing something. It's missing plus minus. Remember, whenever you square root something, there's gonna be a plus minus element at this level, okay?
mm-hmm.
Now, let's graph this function. So you'll see that this is actually made up of x plus 1 and x negative x plus 1. It's made up of two different functions. Root x plus 1, is it shifted 1 unit to the left or 1 unit to the right? The plus 1 there.
To the left.
To the left. So your parent function would look like this. The one shifted 1 unit to the left looks like this. So that's root x plus 1. Negative root x plus 1 is the exact same thing, except it's a reflection. Is it a reflection on the x-axis or a reflection on the y-axis?
The y.
It's on the x-axis. So it flips here, okay? It would be y-axis if it was inside the function. Remember, k is what does the y. K is a reflection on the y-axis, and it's always inside the function, the negative sign. A is a reflection on the x-axis, and the negative sign is also always outside the function. So here,
Mm-hmm.
it's outside, so it would be a reflection on the x-axis. So that's what it looks like. And as you can see, this function, y inverse, fails the vertical line test, therefore it's not a function. But we knew that, right? Because the original function failed the horizontal line test. Cool?
Mm-hmm.
That's the idea behind inverses. It's not terribly difficult. Let's look into piecewise function. What's a piecewise function? It's just a function that has multiple parts, like the previous question. Something like this.
Mm-hmm.
It's a function that has multiple parts or multiple equations. So here we're given a plot. As you can see in this plot, you kind of jump, right? Jump from here to here, and then you jump from here to here, and it looks like you jump from here to here as well. This is what we call a piecewise function. It's made up of multiple parts. Our goal for this question, what's the goal? Is to write the equation for this. Okay? Is to
Mm-hmm.
write the equation for this. So you can always say it's either going to be f of x or y. It's irrelevant what you choose. So it's either going to be f of x or it's going to be y. And then it's going to have multiple parts. It's going to have one equation with its condition. So let's say when x is less than 0. It's going to have equation with second condition, third equation with third condition. And it depends on how many parts there are. In this equation, it looks like there's 4 parts. So this piecewise function is going to have 4 different equations on it, okay? 4 different equations. So let's start. The first one here, that's just a point, okay? That's just a point. So we're going to say y value is going to be exactly 0 when the x value is exactly 0. That's step number 1. Let's focus on this one. What's the y value here? Is it 5, 6, or 7?
It's 5.
It's 5. So y is going to be 5 between which two x values?
0 and 1.
Are they both inclusive?
Not 0.
Not 0, exactly. So 0 exclusive, 1 inclusive. So that's the second piece done. Let's move on to the third. I'm going to say that's a y value of 13. So that's between 1 and 2, right? Yeah. 2 is inclusive, 1 is not inclusive. And now for the final one. What about the final one? How do we come up with an equation for that one? I'm gonna cheat, okay? And I'm not cheating technically. When I say cheat, I mean I'm being like a smart ass about it. This is what I mean. What you do is you pull this backwards. What's the point of doing this? To see what the y-intercept is. What's the y-intercept?
7.
It's 7. So you have something plus 7. Something x plus 7. Now we just have to find the slope, right? And I'm gonna pick a nice point to find the slope. I'm gonna pick this point, and I'm gonna pick maybe this point. Because these are exactly whole number points on the curve. So the rise is from 16 to 22. So the rise is 6, and the run is from 3 to 5. The run is 2. Therefore, my slope is 3. So the equation is 3x plus 7, and that equation is valid. When is it valid? Everywhere? Or does it have a condition?
X has to be greater than 2.
Correct. And there you go. We've just concocted the equations for a piecewise function. Not terribly difficult. You just have to keep in mind inclusive, exclusive, yada yada. And now this one says graph it. How hard could it possibly be? So this one only has 2 parts. And it looks like the number of interest is what? Positive 2, right? So every other
Mm-hmm.
number is irrelevant on the x-axis. The only one you're kind of interested is 2. Now I'm going to be a little bit quick about this because on the top you just have the parent function x squared, which looks like this. At the x value of 2, what's the y value for x squared? It's 4, okay? It's 4. The y value there is 4 for x squared. So how does that help us? So our x squared function is only valid to the left of 2 exclusively, right? So look at this.
Mhm.
It's going to come from negative infinity. It's going to go through the origin. And then right here at the y value of 4, it's going to have an open circle. So that's the top equation done. Now the next equation, 2x plus 3, again, we want to find what the y value is at that point. So 2x plus 3 has a y-intercept of 3, has a slope of 2. So at the x value of 2, the y value will be 7. And this one is inclusive, right? So it kind of looks like that. But for us, the plot is only valid to the right of 2. So at the y value of 7, let's pretend that's a 7. There's a closed circle here, and then I'm going to take this chunk and I'm going to add it here, right here. And there you go. That's the answer to this question. Again, not very difficult, yeah?
Mhm.
Piecewise, nothing really. It's just a combination of two functions. Okay, let's try this one. I'm going to need your help on this. And it's easier than you think. You just have to be able to identify what's this weird looking function. If you identify that, it's very, very simple. How many parts do we have?
3.
We actually have 2 because this chunk and this chunk is one function. What's that function? Remember? It's one of the 7 main functions. Looks like this.
Reciprocal.
It's a reciprocal function, right? So it contains both of those chunks. So that's why this is only a two-parter. So our number of interest, again, just write it down. Our number of interest is 2. On the reciprocal function, it's inclusive and it's to the left of. But the straight line at y value of 2, it's exclusive and it's to the right of. So look at how easy this is. For the second function, that's only y equals 2 when x is greater than 2. For the first one, well, it's y equals 1 over x when x is less than equal to 2, and you're done. That's it. Cool?
Mhm. Mhm.
All right, let's call it there for today.
Okay, thank you.
See ya.